And a class then is by size. Category was by program name, classes are by size. And that's what I was trying to do up there. We had a big memory, big CPU, and 2 big I/O classes. So that's by resource consumption. And also during my interview process, I want to figure out what's the workload type. Am I a compute server? Am I timeshare? Am I a real-time file server, web server? There are 2 types of database servers. Database warehouse, what they call strategic business analysis nowadays. We used to call it data mining. So I may build a database with online transaction processing and have every cash register for Walmarts and every store in the country putting data into an Oracle database. And then at the end of the day, I run the data mining on it and say, oh, northeastern America, they're buying lots of snow shovels. Oh, there's a snowstorm going on up there. Let's send snow shovels up there. So data mining is looking at trends within the database that you've built. Now, online transaction processing is usually lots of little I/O. And then the DBMS, the data mining, is usually large sequential. Maybe my server type is media-based with a video server. I do have sites out there that just do application development. So the developers for Nastran may have an origin there to do additional development of the Nastran application. In our office and in this room, we've got desktop workstations. And finally, there may be graphics needs. For example, if I'm at Disney, being able to visualize the dinosaur movie or something like that would be something that's graphically intensive. So I want to know what type of server it is. Now, we already went through this. This is just talking about bottleneck analysis. And that's reinforcing what I had put up there. As my bottleneck curve, as my number of processes go up, my bottleneck curve gets worse, my expansion factor gets higher. Now, so far, our expansion factors have been in the order of 5. So a 20-minute job might take on the order of 100 minutes to get through the system. Or a 1-minute job taking 20 minutes, or I'm sorry, a 1-minute job taking 5 minutes to get through the system. And one thing you should be aware of is workload variability. The best running systems out there only run 2 or 3 things. And we're in that position. We're running 4 things right now. So the cleanest running computers that I see out there are optimized for 3 or 4 different things. And then when I look at the data, they're tightly coupled classes. As I try to run more and more different things on the system, like a university site, the variability in the workload is going to cause my bottleneck curves to cave in sooner. In fact, this includes the check config demons. All that noise, the interactive user. We don't want interactive users on compute servers because they log in and interrupt my work. So all that variability causes my bottleneck curve to cave in quicker. And that's what I'm trying to show here. The more variable it is, the more classes you have, the more potential problem that these bottlenecks are caving in sooner than they should. And at some point, we don't try to run everything on one system. Okay. At some point, you start offloading things. For example, at NASA Goddard, looked at a system, 20-minute waits on the man page. Through the accounting data, we identified the program as a program called Solve. They first cleaned up Solve and redesigned the I/O on it, but it was still intensive on the system, taking all the buffer cache buffers. So they then moved it onto a different system, where they did not have interactive users starved for file system buffer cache buffers. So at some point, you don't try to run everything on one system, and that's what's happening nowadays, is we get a cluster dedicated to one particular application, rather than trying to run a job mix on that one particular system. And computers are getting cheaper and cheaper, so I can buy more computers and have them dedicated to a particular type of application, and then optimize that system for that application. So with bottleneck analysis, what I'm trying to do is figure out what resource limits my performance, and figure out what's the maximum run limit. If I know how big these things are, then I know how many I can run before I exceed the capacity of my system. For example, code 4. We had 400 megabytes needed by the system, okay? But I only had, it was like a 2 gig memory, 1.5 reserved for misers, so that left me a 0.5 gig there, plus 1.5 on swap. So I only had about 2 gig of real usable swap there, which allowed me to run 4 code 4s. Past that, I run out of memory and I start dying. So bottleneck curves allows me to figure out when's the system going to reach capacity and then do predictions. And there are people out there that will actually collect SAR and accounting data, feed it into a model, and then say, if I double the number of CPUs, will my performance get better? And predict that sort of stuff. And again, we're trying to do improvements to increase capacity. So here's my little bottleneck rules. First of all, every computer has bottlenecks. That will always be true because we deal in finite resources. However, the bottleneck may not be restraining the system. When I take the freeway in California and I'm driving down and I got 5 lanes, if it's 3 in the morning, I'm not bottlenecked. In fact, those 4 lanes could go down to 2 lanes, and if nobody's on the road, I'm not bottlenecked. But if that freeway is fully full, then I do experience the bottleneck. So we may not be restraining the system. Also, more than one resource can be a bottleneck. Okay, we've gone through a couple bottlenecks, but our most expensive one has been memory because of code 4. But I can experience a bottleneck on all 6 resources in the same day. So I can bottleneck on NFS traffic, I can bottleneck on buffer cache. We've oversubscribed CPUs today already, so CPU wait times are going up. But the fatal one was memory, because that ended in death. Different workloads have different bottlenecks. VI is not CPU starved. So when Warren's looking at load levels, that's telling me about my CPU load level, but VI does not need CPU time. Okay? What do we got going on with the system right now? Anything right?
20%, 30%.
They're all code 2s, that's fine. So if I do a W command, my load level is at 5. Okay. So I'm just good response. I'm getting a prompt back for every carriage return. I'm going to do a VI. Good response. Okay. So I just got a reference. The system is behaving responsibly for me right now. Now I'm going to drive up the workload. The only thing I'm going to push on is the CPU time. There's no I/O, there's no memory load behind it. I'm going to run 64 copies of code 2 on top of the ones that you have.
That'll make it go ooh.
But let's see what happens here.
These are big CPUs. Low memory, okay.
Just firing it up now. SAR-Q, 1 space 15.
Oh yes.
So I now have a run queue size, and it's growing, 47, as I fire off more and more work. I was going to get up to 64. So the run queue size looks like, there we go, just about there. So I've now got all those code 4s running. PS-EF, or sorry, EL, rep for code 2. And note, I am getting a slowdown, but it's not too bad. And note that all these code 203s do not have any WCHAN field to them at all. They're all sitting there waiting for a CPU, and most of them do not have a CPU assigned to them. But look at my response. A little sluggish, but not too bad. Okay, CD into /temp, VIXXX. Taking a little bit here now, but not too bad. Open. Okay, that was not a 20-minute wait. Now the code 4s are causing memory bottlenecks, and codes 1s and 3s are causing I/O bottlenecks. But the only thing I've done is push the CPU load on the system. Okay, so different workloads have different bottlenecks. Code 2 is bottlenecking on CPU 8, but my VI was not. Let's see if we can get any data on that. -W-N VI. Must have lost it here. Timing date. I thought that I would have seen it by now. I thought maybe it was in a newer file or something. Let me try ACCOM-NVI -V to go backwards. Yeah, I still don't see the VI. do have a PAC 1 at 15:05, but I just ran that VI in the last minute, so I'm not sure why I'm missing the VI at this point. So I'm just going to ignore that right now. Try other things to look for that command too. But let me just go back now. With the W command, I still see my load average is 64. Divide that by the number of CPUs to get you your CPU subscription ratio. So it's a 16 CPU system, so that's 4 times more processes than I have physical CPUs. Which means these things are going to have to start waiting for a CPU. And if the accounting data is in fact working, when this is done, we'll see the high CPU wait times first thing in the morning.
What are the other two numbers, the 31.60 and 60?
This isn't a smooth number. So this is 1 minute, 5 minutes, and 15 minutes. So it's the average across a larger, what they call a rolling average or moving average, a smooth number. So we're not instantaneously responding. That's what SAR-Q is doing. So SAR-Q is, I looked and it was 67. I looked and it was 67. But over the past minute, it was 64. Or over the past 10 minutes, it was 31. Past 15 minutes, it was 16. So it's just a smooth number of what my run queue length, how many things are waiting for a CPU. So I got 67 things on the run queue and only 16 CPUs. And note right now there's a little bit of I/O it looked like, but very little I/O indicated here. No real I/O contention. Okay. Now, let me do it over here. We're going to come back to this data and try to apply it, particularly if we can get sight from like Warren's machine. I think he said there was a counting there. So some of that data.
I don't know if the counting's on there or SAR. Let me log on and see if he's got counting on.
We'll find out, but just get back to me when you've got that tar file back. So I just need to wrap up here. What I was saying though, different workloads have different bottlenecks. VI was bottlenecking on buffer cache, and Code 2 was bottlenecking on CPUs. A bottleneck is the resource that restricts throughput, not necessarily the slowest. For example, I could have a real slow disk drive on do. Would it matter to me? Code 2 does no I/O, so that would not be important to me. I could have a real slow 5400 RPM drive, but if I don't do any I/O, who cares? Okay. Same thing with file servers. The faster the CPU isn't going to help you much because you're not CPU bound. You're spending all your time waiting on I/O and pushing data across the I/O paths. Different workloads have different bottlenecks.
When you have an I/O problem, what you can do?
Let's save that for now. We'll talk about I/O after CPU. Okay.
Okay. SAR, PCMD, and accounting are all done.
Great.
Anybody else we need?
No. So anyways, I'm just saying that the bottleneck is what's stopping your throughput, not the slowest. Okay, I could be in a moped or I could be in a sports car, Corvette. But if the road's loaded down, it doesn't matter what the speed of my vehicle is. Same sort of concept. Improving bottlenecks eventually causes another bottleneck. So as I solve a bottleneck, there's always another bottleneck around the corner. I've been adding more swap, which allows me to run more code 4s, but eventually the swap I/O traffic becomes the bottleneck. Okay. And again, system capacity is the arrival rate. If the arrival rate exceeds the capacity, the machine is overdriven or saturated. We've got more work than capacity on the system. I just wanted to wrap up here. Resource use by class. This would be something that I find at General Motors. So they take all the accounting data, and this is due to edge effects, where this month something ran short and then it ended in the next month. Here's a month where I started in the middle of the month, but it ended in the next month, so we don't see it until the next month. And the TeamQuest product I mentioned earlier will generate these charts for me automatically. So for every month, I get the CPU hours times the number of CPUs in the system. And in this case, they're breaking it between Army, Navy, and Marines. So if I go to General Motors, I can actually look at a 5-year plan and then look at it projected 2 years into the future. And watch and do a trend, run a statistical analysis algorithm, do a trend projection on it. Now this is the type of data that I was getting out of SPV. This happened to be the NASA Goddard site. So I looked at a month's worth of data on NASA Goddard, and they had over 2,000 jobs. Looks like about 2,500 jobs that ran in that month. And this is the elapsed time, so it looks like about 75% of the jobs are coming in under 8 hours. A few of them were coming in under the 20-hour range, and then we've got a whole bunch that were over a day. Worst case scenario would look like about 130 hours. So this gives me an idea of my user quality of service. Okay, well, how long are my users waiting for their jobs to come back? I can then look at it with the expansion factor. So this is the same set of data, the same 2,500 jobs, and most of my jobs have an expansion factor under 5. But I do have some that are getting bad. In fact, there's one up here at 100. There's another one up here. But now I'm getting references where most of my jobs are coming in a tolerable quality of service. Now, at the time, SPV could not sort by command or queue or user, but now I can, so I can get this chart and use colors to separate the top users and stuff. And then here's my scatter plot that we looked at earlier. So I've got my CPU hours here, and I've got my memory sizes here. Okay, and the better running machines will be tightly clustered. Okay, so I've got a group of processes here, I've got a group here, I've got a group here, group here, group there, group there. So that's 1, 2, 3, 4, 5, 6, 7. Looks like about 7 or 8 classes of programs here. In the Cray world, we actually hired somebody at the University of Wisconsin-Madison to write software that would draw the circles around each of the classes. And this is called workload clustering. And once I've got the clusters, then I can figure out the average, the min, the max, the arrival rate, and feed that into performance models. Also, I want my NQSQ structures to wrap around these classes. So for example, 20 hours would be a bad break within my data. Looks like about 18 hours might be a better break in my data, so that I don't take this class. That's the same program running different model sizes. And I don't want to break that program into 2 different queues. A lot of people with NQS, the queue structures are hand-me-down friendly, 8 hours, 16 hours, 24 hours, 4 meg, 8 meg, 16 meg. But what you really want to do then is say, where are the natural breaks in my workload, and to adjust the queue structures to wrap around those classes. And again, cash flow projection is the best way to describe capacity planning, to project into the future and say, I want to start the procurement process before I get the performance problem. Problems of capacity planning. First of all, standard terminology does not exist. There's no definition of what capacity is. A system can have different capacities. With make part, I can partition it off and change the capacity. I've been calling it a workload unit. There's no other definition. There's no standard way of describing what a workload unit is. It could be a transaction, it could be a web hit, it could be a car crash. There's also forecasting future applications is difficult. You don't know, for example, if Ford, they have to ask their user community to say, oh, you've got a new car design coming up, I better plan on that particular project. So you have to be tied into your user groups. There's no uniformity among systems from different vendors. IRIX and Linux from SGI are both Unix-based systems, but the numbers are different. And if you're doing modeling, model inputs are hard to measure and predict. We are real good at prediction now. We did a performance model study when we were developing the software and found one class of programs that did not fit the actual experiment. They went back and found a bug in the software, and after that was done, the experiment matched the prediction. And this is done with a product called TQ Model. And then there's another company out there called SES that deals with distributed environments. So with SES Workbench and SES Strategizer, I can actually drop in an origin, pick the release, put Oracle on the system, configure Oracle, even specify the release level of Oracle, and then throw an attack at it and see how it's going to perform. And mathematically predict it before I actually build the system. And that's what performance modeling is about, is before I've got that system built, let's make sure it's going to perform as we expect. Anyway, I wanted to finish up that chapter. So we're going to come back to analysis, but the next step now is profiling. And tomorrow morning we're going to spend on applications. But before we do that, the main thing that we're going to want to do now is QSub code 203.NQS And then there is several other jobs that I want us to run. Code 2 prof.nqs is an SS run experiment. And qsub code 2 perf.nqs, which is the perfx command. And that's what we're going to look at first thing in the morning, is SS run reports and perfx reports. Now, we also have to get into multi-threading, so there is also going to be, after the single-threaded version, it's a multi-threaded version of it, code 2 mp.nqs, and then the prof and perf versions of those. Code 2 mp prof.nqs, and then qsub code 2 perf, code 2 mp perf. And all I'm doing with these is a -APO on the compiler. And these are going to be what's called OpenMP. And just to prepare you, take a look at the man page, PE_environ. So that's what we're going to basically spend time on tomorrow morning, is looking at the differences between these runs. Okay.
How many times do you want us to run these
5-6 times.
tonight?
Yeah.
All of them?
Yeah. So we're going to throw them at the system and look for variances in them. I don't want to run just one because I can't get repeatability. Okay, so I want to run them 5 or 6 times to get enough runs to look for the differences between them. And then tomorrow we're going to start, we'll do this again tomorrow, and then we'll start looking at the data. So I'm just giving you something to run for today. You want me to just call it